Happy to have Professor Chris Monahan from Colorado College today to give us a talk on his recent work on this lattice calculation of nucleon structure, especially in the short distance factorization framework. And Professor Monahan obtained his PhD degree from University of Cambridge in 2012, and he started his postdoc at William Mary in 2012 as well, and he became a faculty at William Mary since 2019. And in the past year, in 2024, he moved to Colorado College as faculty. And he also received an NSF Career Grant and a DOE Early Career Award. And he was in 2023, he served on the Particle Physics Project Prioritization Panel, which is P5. And so, we are very happy to have him talk about this, a very recent, new method in lattice calculation of the nucleon structure. And please.
Thank you for that invitation and for this opportunity to talk about some of our work with the HadStruc Collaboration. I'm sorry I can't be there in person, but I hope that I'll be able to visit what looks like sunny California soon. It's sunny Colorado here, so I'm not really complaining. I wanted to talk today about two recent calculations, one of which is ongoing by the HadStruc Collaboration, and to put that in the context of the broader community's goals to try to understand the internal structure of hadrons and the nucleon in particular. So, of course, there are three parts to my talk. I will start by talking about how I think about hadron structure on the lattice. I think this is a way that the community has moved, and then focus on one particular approach to extracting hadron structure from lattice calculations through the examples of the HadStruc Collaboration, and then present two of our recent works, or one of our published works and some ongoing work. So, of course, I'm sure this audience doesn't need to be told that first principles calculations of what's happening inside protons and neutrons expressed in terms of their constituent quarks and gluons has been a long-standing goal for nuclear physics. Protons and neutrons, or nucleons, are really the bridge that ties together the standard model of particle physics and high-energy physics with nuclear physics. And it has been a central focus experimentally in the US at the Jefferson Lab, both through 6 GeV and 12 GeV upgrades, and in the future EIC, which I'm sure is coming on time soon, which will take place at Brookhaven National Lab. So the way that I think HadStruc thinks about hadron structure is in terms of three complementary spaces. The traditional focus has been through QCD factorization, expressed in terms of the momentum fraction space. And this is most naturally accessed when we're thinking about experimental cross-sections, which we can express in terms of some high-energy partonic scattering process convoluted with some non-perturbative information about the target hadron. And that's really what most people think about when they think about the internal structure of hadrons. On the lattice, it makes more sense to think in terms of two complementary spaces. The kind of traditional, represented by this ancient computer approach, is in terms of local operators, or in other words, in Mellin space. But more recently, over the last decade, although it's important to point out that some of these ideas go back much longer, has been in terms of non-local operators, which are most naturally expressed in the continuum in terms of Yoffie time, which is the Lorentz invariant product of this non-local separation in our composite operator with the hadron momentum. Can you see my cursor?
Yeah.
Okay. And there are ways to relate each of these objects. given perfect information about any of them, we could extract information about the others, for example, through Fourier transform or through a Mellin transform. But of course, typically what we have is imperfect and noisy data. So at least part of my talk, I'll be talking a little bit about the HadStruc approach to the so-called inverse problem, which is reconstructing these continuous functions from imperfect or noisy and limited data. So our starting point is this hadronic matrix element. So let me talk about that in a little bit more detail. This is the matrix element between hadron states with some momentum p, which we hope is large, but is typically the order of 1 to 2 GeV. The operator that we're interested in is a generalized operator between, in this case, quark states, separated by some length n, and for gauge invariance joined by a Wilson line in the fundamental representation. And then depending on the kinds of questions you want to ask about what's happening inside protons and neutrons, we may insert different Dirac gamma structures here. So from this matrix element, if we think about it in terms of light cone observables, or variables rather, and the quarks are separated at light-like distances, then we can Fourier transform this object to obtain the traditional PDF expressed in momentum fraction, or x here, space. That is obtained by QCD factorization of experimental cross-sections, for example, of deep inelastic scattering. The alternative is to consider this composite operator in space-like separations and then take a slightly different Fourier transform in terms of the Yoffe time, and that gives us the so-called pseudo-PDFs, about which I will have a comment later. Those pseudo-PDFs can then be related to the PDFs through so-called short-distance factorization, which is really an operator product expansion in this space-like separation. And the final, third of this is the quasi-PDFs, which arise through the large momentum effective theory, or LaMET. Probably pseudo-PDFs and quasi-PDFs are phrases that you've heard even if you aren't working on hadron structure. So here we are studying the same space-like separated operator between hadronic states, but taking a slightly different Fourier transform. There's a typo here, that should be PZ. So yeah, well, I won't really be talking about the quasi-PDFs or the LaMET framework, but focusing instead on the HadStruc implementation of this, which is the short-distance factorization approach. It's not so easy for me to see you, so if you have questions, please feel free to just interrupt. I can't see if anyone puts their hands up, but I'm welcome questions at any point. So let's talk about this in a little more detail and look at short-distance factorization. And I'm going to introduce quite terms that are maybe terms you've heard. I hope they aren't too many technical terms. In part, this is for my own sanity. I always have to remind myself of what everything is. So our starting point is, of course, this matrix element, which is called typically the pseudo-PDF. In practice, what we're interested in is this matrix element in continuum limit and expressed in these Lorentz invariant variables, which are the Yoffe time and the separation squared. And this is the leading twist piece of this matrix element that can be Fourier transformed to directly give the pseudo-PDF. And from the pseudo-PDF, in the limit in which we approach the light cone, that gives us access to the x-dependent light cone PDFs. Now, this limit is not trivial because there are logarithmic divergences. So in practice, you can't just take the limit directly. And in fact, one of the things that I want you to take away from this is that we don't actually ever use the pseudo-PDFs. So we talk about short-distance factorization rather than pseudo-PDFs because short-distance factorization provides the framework for extracting hadron structure in terms of Yoffe time, and the pseudo-PDF never even actually enters. So in practice, what we do is we do a lattice calculation more of which later, of this matrix element. We're interested in isolating this leading twist contribution, and that has UV divergences. So we use the so-called ratio method to construct a renormalization group invariant combination of these leading twist objects. Here we have the zero momentum version, but with the same space-like separation. From this ratio,
Chris,
sorry, go
can I
ahead.
ask a quick question?
Of course.
So in the matrix element definition, your nucleons, your states, they in principle also have spin degrees of freedom, right? It's a spin 1/2 nucleon.
Sure.
Do you have to project into specific spins? Is this just in diagonal spin space? Do you have different...
that depends. That will depend on what, excuse me, you're interested in. So, I mean, I've been talking generically about unpolarized distributions, in which case you're averaging over initial and summing over final states.
I see.
But if you're interested in the transversity or helicity, then yes, you would have to isolate the spin components appropriately.
Okay. Okay. Thank you.
Sure. Also, hello, good to see you. So from this ratio, we are interested in this short distance limit. So everywhere you see pseudo, that means that we're at space-like separations. The Ioffe time distribution, which is a direct Fourier transform of the x-dependent PDF, can be related in the short distance limit to this data that we have from the lattice. And it's related through this perturbative convolution. So our goal is to extract this Ioffe time distribution, which is on the light cone, but it's a convolution and therefore poses an ill-posed inverse problem. So in practice, what the HadStruc collaboration does is we have several options, but the most basic thing that we have tried really is parameterizing this PDF. The Fourier transform of this PDF can be calculated analytically or numerically, and that gives us this Ioffe time distribution, which we then relate through perturbation theory to our lattice data. So the idea is to fit our lattice data to a convolution of these parameters. Here are two very basic common fit forms. And expressed in this way, it's really the same issue that we have with experimental data, where on the left-hand side, we have experimental cross-sections. We have a convolution of some PDF with a known perturbative hard scattering kernel, and different global fitting collaborations choose different methods, such as parameterization or neural nets and so on. So this ill-posed inverse problem, something that I would want to stress is that this applies to any lattice calculation that is interested in extracting continuous functions related to hadron structure. And I'm sure many of you are familiar with inverse problems, but broadly stated, they are widespread across the sciences because they're really just trying to observe, or rather infer, the causes from the effects. Mathematically, this can be expressed in terms of a forward map, where we want some model parameters that, given this forward map, match our observed data. So in this case, we have some lattice data. We got some parameters, and we would like to infer those parameters and the model that corresponds to the QCD physics we're interested in. And this is ill-posed, at least in the classical sense, or rather it's well-posed, I think I should say, if there exists parameters that fit the data, and if they are mapped uniquely to the data and smoothly. So that's the traditional classical definition of what we mean by ill-posed inverse problems. A lot of the literature kind of conflates inverse problems and assumes that they are ill-posed, but they can have well-posed inverse problems. We just don't tend to find them in lattice QCD. Of course, the situation that we're dealing with is very much not ideal. We have data that are statistically noisy. Here is just a sample of some gluon data. We would be interested in the Fourier transform of this object. And necessarily. There will be systematic biases. For example, these data appear at just a single pion mass, which is unphysical, and at a single lattice spacing. And if we are trying to take the Fourier transform with respect to this Yoffe time, the argument nu, then this is a Fourier transform from 0 to infinity, and 7 is definitely not a large number. So we have a very limited kinematic range. And the Fourier transform is therefore definitely an ill-posed inverse problem. It's neither unique nor stable. And one of the reasons that it's not stable is the presence of noise. So any lattice calculation will have statistical noise, and that typically leads to a failure of stability in your reconstruction of the forward map. So broadly speaking, there are kind of three ways to deal with this ill-posed inverse problem. You could try to reduce the noise and obtain more accurate data. That may make your reconstruction more stable. In other words, you can find a smaller range of parameters that give rise to our observed data, our lattice data. You could change the map and acquire different data. But both of these methods are not really available to us in the lattice community. We have, what we call high precision data is not really going to be high precision in the context of an ill-posed inverse problem. And our map is given by the non-perturbative dynamics of QCD. So we are limited by our ability to carry out lattice calculations and by the dynamics of QCD. And so really the main option that is most realistic is to think about restricting the space in which you look for parameters. In other words, you need some kind of prior model or some extra assumptions. Those can take two different forms. One is like a penalization procedure or some kind of regularization, Tikhonov regularization, Backus-Gilbert, or more generally, a Bayesian framework in which you have a prior model and you are interested in the likelihood of the posterior distribution based on your observations and your prior model. Broadly speaking, I think many authors would consider the first of these options to be some kind of subset of the second one. But the Bayesian framework brings with it the advantage that you're really making explicit the fact that you are introducing a prior model. And it can make more explicit the impact of the prior information that you have included. So in this context of three kind of broad strategies, there have been many attempts since early methods by Wang and her co-authors to directly Fourier transform, to use some different filtering methods. More advanced reconstructions have been have been used and are continuing to be used. But the primary processes that we have used in the HadStruc collaboration is kind of a global fit approach with a parameterized model, or through Gaussian process regression. I have not been involved in that work, so I won't be discussing that in detail. And one of the things that we'll be advocating, so I'm kind of advertising a paper that should be coming out at the end of this week or early next week, is how important model data enclosure tests are when trying to understand how effectively our methods work. So this is one of the first works that I'm aware of by my colleagues. I was not involved in this in the HadStruc collaboration, where they studied two different PDFs and analyzed various reconstruction methods, some of which worked okay, I would say. But the more important point, I think, is some of the conclusions. So the more advanced reconstruction methods leads, to quote this paper, to satisfactory reconstruction results for Bjorkane X above 0.1, which is relatively large by experimental standards, if you have Yoffe times up to about 10. And if you aim to double that Yoffe time, then that could be reasonable and achievable in the near future. This paper was written 5 years ago, and it has not happened. But in 5 more years, perhaps it could. But it does say that tripling or quadrupling the maximum Yoffie time accessible would require a concerted effort, sorry, I'm missing a word, by the Lattice community working on PDFs. In other words, for the near future, the takeaway from this is that we kind of stuck with what we have, and that maybe you can improve your Yoffie time range by a factor of 2, but much more is going to take, the same timescale as the construction of the EIC. So, this is an area of active research, and something that I think I would stress is that the inverse problem is a significant challenge, perhaps the most significant challenge, and it's faced by any approach to extracting hadron structure through non-local operators.
Hi, Chris.
Yeah.
If I want to go to x as small as 0.01, how large a Yoffie time needs to be? 100 or 50?
So I don't know. It doesn't scale linearly, I think, right? So I don't know exactly, to be honest. I mean, it roughly goes like 1 over the Yoffie time. So if you wanted to reduce x by a factor of 10, you would arguably need probably a factor of 100 Yoffie time. I mean, rather up to Yoffie times 100, but I'm not sure it's exactly 1 over 10.
Exactly.
Yeah. That is probably unreasonable. It's probably not feasible in the near future. And in part, which I didn't emphasize, that's because in this framework, we require small distances of, say, 0.5 Fermi, and no more than 0.5 Fermi, roughly. And so, that might be, but then you need very large momenta, unfeasibly more than 10 GeV, to reach Yoffie times that large. So at the moment, we're constrained to 2 to 3 GeV, and even then we find that we have difficulty extracting signal above 2 GeV. Okay. So I wanted to share some of our results. One was our moments of nucleon GPDs, which were published last year. And then to wrap up, I'll talk about an ongoing project that I've been working on with a graduate student at William & Mary, Alex Sturzu. So I haven't put a ton of Lattice details into this, but I have some backup slides if people have questions. Our work here has been carried out on this single ensemble, lattice spacing just below 0.1 Fermi, pion mass of 358 MeV. We use just 4 time sources, which we can get away with on 350 roughly configs because we use distillation. This is 2+1 Wilson Clover ensembles, well-known ensembles from JLab, William & Mary, Los Alamos, and MIT. And we use distillation. And then in the work that I will show, we have done the analysis of correlators using both the summation method and 2-state fits. So this uses just a single source sink operator. So when this doesn't include the GVP or any kind of variational method, is what I meant. And that is sort of ongoing because one thing that I will show is that we have significant excited state effects. And that's one of the dominant sources of uncertainty in our results. And so we're exploring the variational method as an approach to try to improve our signal. So before I get to all of that, GPDs are really 3-dimensional measures of the internal structure of hadrons. So there are 2 broad ways of thinking about what's going on inside the proton or neutron. And that is to ask questions about whether the correlations between the quarks and gluons in the transverse momentum plane, which gives us the transverse momentum dependent PDFs or TMD PDFs, or in impact parameter space, which is, roughly speaking, the distance from the center of the proton or neutron. And so GPDs tell us about correlations in this impact parameter space between the longitudinal momentum of the hadron and between the transverse impact position of the quarks and gluons. And it's a long-term goal for the nuclear physics community to be able to understand these correlations and to make pretty pictures of what's happening inside the three-dimensional structure of protons and neutrons, and one of the central goals of the EIC. So to summarize our results, we did not provide a reconstruction of the GPDs themselves, but we provided the first calculation of moments at non-zero skewness. So we provided them in this kind of digestible format, which was expressed in terms of a dipole fit. However, our data is publicly available at Zenodo, and there we have a more sophisticated analysis. This is just a common way that the community expresses these results. So we have, I should point out, no continuum limit. There is evidence of discretization errors, as you'll see in one of the plots. And we're at unphysical pion masses. That's also visible in the data I'll show you. Nevertheless, these are the first moments of the GPDs at non-zero skewness. And if you, if you wanted to play with the data, they're available publicly. So one of the challenges for GPDs is that they just is the span of kinematic region that you need to get any information. So we had 186 pairs of initial and final momentum, corresponding to 116 points in the skewness zeta and momentum transfer t planes. So that's expressed here on the right. And then on the left, this is the Yoffe time, which is like the average momentum dotted with the separation of the composite operator. And this is, of course, an enormous kinematic coverage, relatively speaking, distillation. But nevertheless, it's not enough data to reconstruct GPDs. So there's an inverse problem in the PDFs, and it is considerably worse in GPDs because you now have a three-dimensional object that you're trying to reconstruct from this limited noisy data. So GPDs are pretty much defined from very much the same matrix element that we saw before, but this is the light cone case. They're defined at non-zero momentum transfer. And this object can be expressed in terms of its Lorentz decomposition in terms of the H and E GPDs. And then they can be obtained in a similar fashion as we obtained the pseudo PDFs, or rather the pseudo GPDs can lead in the limit that the space-like separation of the fields goes to 0 to the light cone GPDs. So we use a decomposition that it isolates the Lorentz structures, and then in the limit that we move towards a light cone, we reconstruct the GPDs from linear combinations of these Lorentz invariant amplitudes. Of course, they're only Lorentz invariant in the continuum limit, which we don't have. And from these, you can construct the generalized form factors. They're basically the moments of the GPDs. And this is what the results that I showed you are. So they are X-weighted moments of GPDs, here given explicitly for the HGPD. And this is the leading ordinary elastic form factor that we're used to. So the elastic form factor arises in the local Euclidean limit. So as we take that long composite operator to become a local operator at z equals 0, Then we can extract the elastic form factors that describe the interactions of a photon with a proton at relatively low energies. And we can access them in two ways. You can either calculate them directly using this local operator, which is, of course, the traditional method, or you can look at the limit, understanding that there's a logarithmic divergence here. So this is a factorization limit of our non-local generalized form factors. And the agreement of those two approaches, or otherwise, gives us a sense of the systematic uncertainties associated with our short distance factorization approach. So here's our first set of results. And this term, A phi, it should be 0. And this is a clear evidence that there's some discretization effects, basically, that's causing this to be not 0. So you would hope that if this were repeated at final lattices and we took a continuum limit, this should ultimately agree with 0 within errors. Here we see a comparison of our local elastic form factors with the PNDME collaboration. We've just plotted selected data here. They have many more data points, but the difference here is ascribable to the fact that they have a lighter pion mass. And this is the momentum transfer. So this is the typical plot that you would see of elastic form factor expressed as a function of the momentum transfer. And we have good kinematic courage, but there's evidence here of chiral effects because this is actually carried out at the same lattice spacing. Another check that we carried out was to look at how our non-local results gave us the equivalent form factors as the local. And you can see pretty good agreement. So these are the results at different non-zero z's. And the quadratic fit to the spatial z dependence gives us the blue points, which broadly speaking agree within errors with the local result. And then this is a dipole fit to both of them. And you can see that broadly speaking, we find decent agreement between these two. Certainly not as much as the chiral effects that we saw in the previous plot or the discretization effects in the plot before that. So here is one of the plots that we use to argue that we have significant excited state uncertainties. So this is something that we are looking into because it's a dominant error in our results, at least a dominant systematic error. And I think it's reasonable to assume that it's a dominant effect in many nucleon calculations. This is well known from, for example, the axial charge. And it's something that all collaborations should be thinking about carefully when extracting hadron structure. So here we have two different fits. These are fits to these lattice data using a simple dipole and then using a Z expansion. So those are the basic fits, red and blue, and they're in broad agreement. They overlap for most of the range, although you can't see it in this plot. Then we looked at two different approaches to the excited state systematics by studying the summation method and by doing a two-state fit. And so the difference between the summation method and the two-state fit propagated through the analysis gives us this band for the excited state uncertainty on the dipole fit. And this band, the green band, is the excited state uncertainty on the Z expansion fit. And so you can see this clearly dominates other sources of error that are given here, which excludes discretization and chiral effects, but nevertheless, it's the dominant systematic on this particular ensemble.
It doesn't look so bad, no? I mean, you can see it, but in the region where you don't have data, right?
I suppose, yes. I guess I'm drawn to this region where it's twice as big, but you're right. There's no data here. That's true. That's a fair point. Nevertheless, I think it is the dominant systematic.
Gotcha.
If you look in this region, if you can see my cursor, it's roughly a factor of 2 larger than the rest of the systematics put together as propagated through the Z expansion fit.
Do you remember, like, off of the top of your head, like, what's the effect on the quoted individual matrix elements? Like, what if you did a summation method versus like a 2 exponential fit, like what's the order of magnitude effect on the individual matrix elements as opposed to like the global fit?
Yeah, no, I don't know. We'd have to go back and look at the paper, and I don't have that information. I might have it in a backup slide. I don't think so.
Okay.
Yeah, sorry. Okay. So the final kind of plot that we made, which I would argue is primarily advertising, is the impact parameter distributions that allows you to make. So this is actually the moments of the impact parameter distribution, not the distributions themselves. But it allows you to make pretty pictures of how the quarks are spread out inside the proton, or in fact, the moments of that distribution. And yeah, very important for advertising and talks. So in summarize, we have calculated the first non-zero skewness moments of the E and H GPDs, the unpolarized isovector quark GPDs. All of our data are publicly available. So you could go ahead and answer that question yourself, Raoul, if you wanted to do the analysis.
Will do.
And we studied the Mellon moments through 186 pairs of initial and final momenta corresponding to 116 different kinematic points, which is only possible with distillation. We found evidence that excited state contamination was a significant systematic uncertainty, and that has motivated a future variational method approach that's currently being carried out. But more generally, I think this work illustrates the challenge of the inverse problem here, which is kind of a looming uncertainty that can only be truly understood once we have control of continuum discretization effects or continuum limit, the chiral effects, and our ability to take the small distance or short distance limit to reduce higher twist and perturbative corrections.
Hey, Chris, can I ask a question?
Of course.
So I was wondering, so the Mellin moments calculation was done on just a single discretization, right?
Yes. A single lattice?
Just a single lattice spacing, yeah.
Mm-hmm.
Oh,
Yes.
okay. Yeah, it's interesting to see. So when we did this calculation in the, normal, like not normal, but like the direct way,
Mm-hmm.
computing like matrix elements of the energy momentum tensor for the flavor vector, there are 2 different irreducible representations that you can use. One for like with the diagonal components and one with the off-diagonal components. And specifically for the flavor vector, like the isovector B form factor, we actually found that just for this specific form factor, for this specific flavor combination, they were like the results were quite different between the 2 irreps, which was very surprising. And we also just did this on a single lattice spacing, so we didn't really have any other explanation for this besides it being due to discretization effect. So I'd be very curious to see like how, I guess with your approach, I would expect to have like a better controlled result. So to see how the continuum limit eventually shapes up for this.
Yeah, absolutely. We computationally, this is going to be very expensive to take a proper continuum limit. I mean, in the near future, the best I think we can do is to have a slightly smaller lattice spacing, like 0.07.
Uh-huh.
Do you have plans to repeat your analysis on final lattice spacings?
I don't think so. I mean, I think this was during my PhD work, so we didn't have any plans to repeat it because it was already so expensive. But I'm just waiting for others to do it so I can finally find out why we were getting this different result. But yeah, thanks.
Yeah, I mean, we have this vanishing term that we found to be non-vanishing when we ascribe that to discretization effects. So it does seem to be an issue,
Okay,
probably slightly different, but related.
I see.
Yeah.
Yeah, sounds good. Thank you very much.
Thank you. I will say that I'm taking part, sorry for this discursive tangent. I am taking part in the writing of the PDF Lattice workshop report, which is this, broadly speaking, something like a community white paper that we work on every 3 years or so. And it is an ongoing topic of conversation in the community whether efforts should be focused on calculating new observables at unphysical parameter values, such as one lattice ensemble with one pion mass that's unphysical, or dedicating time to really taking full control of all systematic uncertainties of the most basic quantities.
Both. Doing both.
So both, yeah, sure. With current funding, if you can do both, then I applaud.
I know.
Yeah, anyway. So I wanted to talk about work that's being carried out by Alexandru Sturțu, who is a graduate student at William and Mary that I have been working with and continue to work with here. And this is, in some sense, a much simpler calculation, but in practice is well known to be a difficult calculation on the lattice, and that's the gluon momentum fraction of the nucleon. So this is a Mellin moment of the unpolarized gluon PDF of the nucleon. It tells you roughly how much momentum is carried by gluons at a given scale. And if you look at this comparison plot from a couple of years ago, you can see that the experimental status is pretty good. Broadly speaking, many collaborations agree within their quoted error bars, and they all roughly agree that it's maybe something around 0.4 or slightly higher. Whereas on the lattice, we have a range of different results. I think this plot probably could be updated, but anyway, these span some smaller values on a single lattice spacing, some values in the continuum limit, and there's no clear pattern at present, nor is there comparable precision with the experimental extractions. Sorry, yeah.
Are the lattice ones of the physical point or extrapolated or heavy quark masses?
I think these are physical pion masses, but I'd have to double check. Cafe may know about this one.
Well, because there are several issues there. One is, of course, the data itself is noisy. The second one is you have to normalize it, mix with the mixing calculation with the quark. Normalization of gluon on the gluon propagator is very, very noisy. There are 3 noisy points. Thirdly, you have to guarantee that because nobody has this conserved curve of quark glue. So it depends on how you besides realization of a normalization, make sure you have momentum and angular momentum and so on to satisfy. So all these turn out, that's what we have this moment. We'll try to do a better job.
But you answered everything except the question I asked. What is the quark mass?
Sorry?
What is the quark mass?
Oh, well, the quark mass we have is 170. That's
170.
Yeah, 170 MeV, sorry.
Okay, so pretty close to the physical.
This is reasonably close.
I think this one is physical just because it's on the milk ensemble, so I think they have access to physical pion masses.
Cool. Yeah.
And so I don't know the pion masses for these ones either. But the situation is probably worse for the pion, in part because we have fewer experimental data, but we also have fewer lattice calculations. So really, this is still an area of ongoing understanding and exploration for the lattice, and in the case of the pion, for the global fitting community and experimental community. So, as Cafe just said, these calculations are very noisy. Here is a plot that you saw before. This is the unpolarized gluon distribution expressed in Yoffie time space. And you'll notice that it's fit exactly to 1, and that is because we use the ratio method for renormalization. And the ratio here is taken with a matrix element that corresponds to exactly the nucleon-gluon momentum fraction. So here we don't know the overall normalization of this Yoffie time distribution. The normalization is given by exactly the quantity that was shown in the previous plots. And this is actually true also for our polarized gluon distribution, where the data are even more noisy. And in both cases, although it's not expressed explicitly here in the plot, in order to get the overall normalization, we need information on the gluon momentum fraction of the nucleon. So that's a kind of internal collaboration motivation on top of our physics motivation for understanding the basic properties of protons and neutrons. Oh, hello, I have a visitor. No problem. Not just now, thank you. So yes, we are interested in extracting the gluon momentum fraction. And the procedure that we use for renormalization here, again highlighted by Cafe, is the gradient flow. So this provides us with a method for controlling the signal to noise ratio because it gives us a controlled continuous smearing. And it also allows us to extract the quantity in the continuum limit because for observables of gauge fields that are at finite flow time, they are finite even in the continuum limit. So one of the advantages, or several advantages on top of this, is that this is a gauge invariant procedure. So it means that we don't have to consider non-gauge invariant operators. And we kind of get it along for free because our local operator is part of the data that we already have from our non-local calculation. In addition, the relevant perturbation theory at next to leading order is available thanks to Robert Harlander and his group. And it is possible that that should be it. NLO is likely to become available. And separately, a topic that I'm interested in is working on a gradient flow scheme for non-perturbative running to higher scales, where we may not need such high order perturbation theory. So the gluon momentum fraction can be extracted from the energy momentum tensor. And I would like to point out that we are neglecting the isoscalar quark contributions in this first analysis. So again, at this point, I feel like I'm just repeating Cafe's comment. We are neglecting isoscalar quark contributions, and we have studied 2 different possible operators, which can be used to access the gluon momentum fraction. In practice, we've found, which aligns with previous results in the literature from ETM and others, that this method, which relies on non-zero momentum, is too noisy. And so we use this second operator, OB, which can give access to the gluon momentum fraction of the nucleon at 0 spatial momentum. So the key addition that is new here is to do this at finite flow time, and that can be related directly through some kind of operator product expansion, which is called the short flow time expansion. And this short flow time expansion relates our float operators, which are calculated on the lattice with hadronic states, to the corresponding renormalized operator in, say, the MS bar scheme, which is the object we want, through coefficients that can be calculated in perturbation theory, provided this physical scale tau, which corresponds to the flow time, is a perturbative hard scale. These coefficients have been calculated already because the energy momentum tensor has been studied by several groups at finite flow time. And so here we do have some kind of choice. So the flow time is something that we obtain in lattice units on the lattice, but there's an arbitrariness to how you relate that to the renormalization scale in the MS bar scheme. And at next to leading order, the natural scale is to choose a relationship like this, which allows us to remove the logarithms from the perturbative matching coefficients. So one of the reasons that I'm not presenting final results is that we are still in the process of discussing how best to associate a systematic uncertainty with this choice of scale. So a typical method might be to multiply this scale by 2 and see what happens. That's often done in perturbation theory. But whether that's the best way to do it is something that we are discussing. So the results that I'm showing are again on this same ensemble, and they're at an unphysical pion mass at a finite lattice spacing. And these results show the matrix element as a function of Euclidean time and analyzed using Bayesian model averaging. Bayesian modeling averaging allows us to mitigate the possible bias of a choice of correlator function by systematically, in this case, removing data and studying how that affects the fits, and then including that as part of the weight that we attach to each different fit that excludes different data. So all of these results are preliminary, and they have been carried out by Alex. And the result that we end up with is a set of data that correspond to the gluon momentum fraction of the nucleon at finite flow time. And this has to be related, so this is a function of the flow time, this has been related through some choice of scale matching to the MS bar scheme through the short flow time expansion. And at the moment, our work is still preliminary, so we aren't quoting numbers yet. But we hope to have results at QCD evolution, which is happening in May at JLab. Okay. So that's our ongoing work to extract the gluon momentum fraction. That's important both for physics reasons, to understand the basic mass and spin composition of the nucleon. In our HadStruc approach, it serves as a normalization or renormalization factor for these ratios that are renormalization group invariant. And so in order to extract that normalization, we need to know the gluon momentum fraction. This is well known as a challenging calculation on the lattice, with not the best agreement between current results and large errors. And so we are using distillation. Alex has now implemented a variational method and is studying the best operator basis for this. And the main method that we are using to control signal to noise and to relate our finite lattice result to the MS bar scheme is the gradient flow. And we're hoping that we can have some public results soon. So that brings me to the end of my talk. To summarize, the way that I think about hadron structure is really in terms of 3 complementary spaces. Traditionally, that has been thought of in terms of X or momentum fraction space. That's most natural in an experimental framework or through the analysis of cross-sections using QCD factorization. But on the lattice, it's much more natural to think about Yoffie time or Mellin space. Short distance factorization is the framework that HadStruc uses to give us non-perturbative access to the Yoffie time distributions, and then reconstructing X-dependent hadron structure from those data on the lattice is an ill-posed inverse problem. And this is really a problem both for PDFs, but much more for GPDs. And I would, if you take nothing else but this point from this talk, there is no method that can allow you to access PDFs right now from Lattice QCD without some assumptions that are used to solve this ill-posed inverse problem. Broadly speaking, community-wide, well-controlled calculations of these kinds of quantities are still several years away, for the simplest ones to decades away. And I illustrated some of the progress that we've made in the HadStruc collaboration through both the GPDs and the gluon momentum fraction of the nucleon, which is still underway. So thank you very much.
Any questions?
I have another question. Sorry, Chris. I think you mentioned, but maybe I didn't pay attention right there. I missed it. This gluon, this momentum of the gluon, this leading coefficient of the gluons. These are for pions or for nucleons or for both?
Oh, this is for our calculation is for nucleons.
Okay.
Yeah. We are also doing the pion calculation, but that's sort of behind the nucleon in terms of maturity of calculation. We're just starting to generate data for that.
I see. So the GBP that you talked about is nucleon pion operators?
Yeah, Alex has been using a 9-operator basis, and I don't know the details of the 9 operators.
They're local.
Do you know if they are local or if there's none, like 2 hadrons also?
That is a great question. I think so. I have to look at Tanjeeb's paper because he also studied the 9-operator basis. I think there are some non-local operators in there, the 2, but I don't remember, to be perfectly honest.
Okay.
But yes, one of the data that showed the unpolarized gluon, that was done with the variational method, and so we could easily look there.
Can I ask a question about the mixing with the flavor singlet? So I guess using in the matching factors that were calculated by Harlander and collaborators, they have also included like the mixing, right? So
Yes.
technically all of the pieces are there to include it, except of course the calculation of disconnected diagrams, etc., right?
Yes.
Okay.
Exactly right. And we are, as a collaboration, but not Alex, are working on those disconnected pieces. We have data, it's being analyzed. So that is part of the project, but we're probably looking to do the momentum fraction as a separate calculation first, and then do a complete calculation of all the scalars at once when the isoscalar disconnected pieces are ready.
Yeah, makes sense.
But yeah, you're absolutely right. And so another piece of the conversation that we're having is a fair way to represent the systematic error associated with neglecting those disconnected pieces.
Right.
Which in the literature is claimed to be small, but we would like to do a bit better than that.
Okay. Any other questions?
Maybe I ask. Can you go back to the slide of the xg dependent on the tau, the momentum fraction dependence on the tau?
This one?
Yeah. Can we get some intuitive idea of what it suggests of the actual xg, or the matching is just so complicated that we don't see anything? Like, can we just conclude something like 0.4 to 0.8 for the xg here, or the matching is so complicated that we don't get anything from it?
No, I mean, ultimately, the matching boils down to a single number. So it's really a multiplicative number. That is, it's close to 1. I'm not going to quote a result because that would give you a result for xg at mu equals 2 GeV. But it's a number less than 1, and 2 GeV I think falls somewhere here-ish. I can't remember exactly. I think it's here. Of course, that depends on how you choose to relate the two scales. But yeah, if you multiply this by a number less than 1 around here, then you get the answer.
Yeah, thank you.
Sure. Also, those perturbative coefficients are available as Mathematica files from Hollander, so it's not too hard to turn those data into an actual number.
Do you have an estimate of what is the systematic from, for example, I guess you mentioned that one way to approach like the scale, the choice of scale matching was to double it and see how things change. Do you have any estimate at this moment of how the systematic is increased by doing that?
Well, no, I don't. The subtext is that me and Alex are have differing opinions on this. And so this is a productive internal collaboration conversation that's happening as we speak.
Makes sense.
Yeah. But I mean, we have all the data, and so we really are at the stage where we are like thinking about systematic uncertainties and the best possible way to estimate systematic uncertainties. And this is a problem, of course, that is a universal problem in perturbative QCD calculations. And as far as I'm aware, they don't really have a better way of doing it than just multiplying by 2 and seeing the difference.
Yeah.
But if you have information on like a good way to do this, I would love to hear it.
I was hoping the same for you.
I don't think, yeah. So my former postdoc, Tobias Neumann, is now at SMU, and he is a high order perturbative QCD expert. And as far as I can tell from him, multiplying by 2 and seeing the difference is really the state of the art.
Sounds like they're
Sometimes we multiply by 1/2 also.
Yeah, I don't want to do a disservice to the community.
All right, thank you.
Okay, so let's thank the speaker again.